Hey, good morning, my chemistry students. This is Mr. Kinney. We're going to go over the first 15 questions on the periodic table test review, and then I should have another video for you for the other ones. Let me zoom out here so we can see the full page. Okay, so starting off with the kind of the way that the theory of the atom, we had the Greeks' idea that there was an atom was the smallest particle. Maybe imagine a sphere. And then around the time, about 200 years ago, Mr. Dalton came up with four main ideas and for chemistry, and this was really the beginning of chemistry. And the first idea was that elements are made of atoms. So elements made of atoms, and that was really from the Greeks. Next thing he came up with, he said that atoms, I'm just going to use a capital A now for atoms here and a capital E for elements because I don't want to repeat. Well, let me get that back over there. Sorry about that. So basically he just said that atoms of an element are identical. Meaning that every atom of gold is just like every other atom of gold. Now, he didn't know at the time that they had the same number of protons, but that they were the same, that there wasn't a difference between them. Now, we take that for granted now, but that was a big deal. And then he said that atoms can join together to make compounds. So atoms join together to make compounds. Okay, that was a pretty big deal. And then he also went on to say that these compounds that are formed, let's say that these three atoms over here, let's see, AAA, let's say those are all oxygen. O3, that would be like ozone. But maybe one that's a little bit better, let's take H2O. Mr. Dalton said that any compound, you're always going to have the same ratio of elements to each other. So water will always have 2 hydrogens to 1 oxygen. It'll always be the same. And so he had the idea of whole number ratios. So that really was the beginning of chemical bonding. And one of the biggest things he thought too is that you cannot, he thought that you cannot change, let's say, lead, which symbol is Pb, into gold. That was a big thing that alchemists, that was silver, sorry, into gold, Au. So this is what alchemists were trying to do for centuries, and he realized you can't do that because lead is always going to be lead. You can never change into another element. That cannot happen. That was a big principle of his. Now later on when we got atomic colliders and we figured out nuclear fusion, we learned we could do that, but for basic chemistry, this will not happen. You're not going to change one element into another. Now, Mr. Thomson's idea of the atom, by this time, Mr. Thomson did some experiments, and if we take the circular idea of an atom, Mr. Thomson did some experiments, and he found out that by shooting these particles through a cathode ray tube, he figured out that the atom has, the outer part anyway, was negative. So the outer part of the atom was negative. And he kind of was credited with discovering electrons. Discovered electrons. And then, so what they thought, now they knew that the overall charge, the whole atom is neutral. So they kind of speculate, okay, there's these negative charges on the outside, and then the rest of the atom in here, which I'll color in green, if you can make out the color, is just kind of an amorphous blob. Amorphous means no shape, but kind of it was positive charge inside, but the whole thing kind of spread out all over because they knew the overall charge of atoms were neutral, but they figured out the outer part was negative. Well, now along comes Mr. Rutherford, and Mr. Rutherford's idea was, okay, he was going to take his Thomson's idea of the atom, and with gold foil, because gold could be pounded fairly thin, so you could get atoms almost maybe 1 atom thick, not quite, but that was the idea. So when Mr. Rutherford was shooting these alpha particles, which is really just a helium nucleus, was shooting these through, and Mr. Rutherford figured out most of them went straight through. That's kind of what he figured. Okay, and so one of the conclusions was the atom is mostly atom, mostly empty space. Now, when Mr. Rutherford was doing this, I'll use a different, occasionally some of these particles would hit something and bounce right back. Now, in order for a big heavy alpha particle to bounce right back, that means it would have to have been repelled by a very strong positive charge. So what he figured was that, let me redraw, he figured now if this was an atom, that there was a little tiny, dense, heavy, positive, what they now call the nucleus. And that was the thing that occasionally some of these particles of alpha particles would bounce back. So now, found out that there is a nucleus that is positive and dense. Dense means really heavy and thick and solid and like that. So that was what Mr. Rutherford, now he didn't discover protons, but he theorized, well, he kind of figured there'd be particles in there, and then they kind of were theorizing then, since he added up how many positive charges were in a nucleus, he found out, hey, the weight isn't quite right. You know, this atom is heavier than the positive charges, so he kind of figured, hey, I think there's probably going to be neutrons, and then Mr. Chadwick, one of his students, came along and did that. Now, with Bohr's theory of the atom was pretty much, when we come over here, you know, they figured up here that, okay, electrons are spinning everywhere, that there's electrons out there. Mr. Bohr kind of came up with a couple ideas here. First off, that there's energy levels, what we might call the orbitals, at certain fixed areas, that there's a pretty high probability that you're going to find some electrons here. But not just this nice gentle racetrack. What Mr. Bohr really found out was that, okay, you have your first energy level here, then the second energy level isn't going to be quite as far. This distance here is a little bit less than this distance. And then as the atom shells, energy levels get further out, they get a little closer to each other. So kind of an analogy was, it wasn't, the electrons were not arranged like a typical ladder that we think of, but imagine a ladder where the first couple of steps, you got to take a really big step to get up there, then kind of a semi-big step, and then it starts getting easier to go up. And that was the idea really of energy levels. Okay, so that, because he was experimenting by adding energy to these and measuring how much energy it took when the electrons got pushed up to their excited state. And then when the electrons would drop back down, he could measure the energy drop. And that's where he came up with the energy levels by using that. And then the Bohr model for carbon. Okay, well, the nucleus, I'm not going to worry too much about that. But carbon is in period 2, so it's going to have 2 shells, 2 electrons. Carbon's atomic number is 6, so there's going to be 4 electrons out here. And so it has 6 protons and 6 neutrons, which we get by 12 as the atomic weight, minus the 6 protons. And then for silicon, silicon is in group 3, so it's going to have 3 shells, and it's got 14 electrons, so we're going to have 2 electrons, 8 electrons. Now the next orbital can only hold up to 8. Now this one can really hold up to 18, but the first part of it's going to fill is going to go up to 8. But here we have 10 electrons, 4 electrons there. So that's going to be, let's see, protons will be 14, and neutrons is going to be, oh, wait, let me get my periodic table here. 28 minus 14 is going to be 14 neutrons as well, in the most common isotope. List the charge, mass, and location of the 3 subatomic particles. Oh, geez, I sure hope I didn't look at the screen. I hope you were able to see the diagram there. Well, you've got pen. And we've got positive charge protons, negative charge electrons, 0 charge neutrons. These are in the nucleus here, and these are out in the shell. Explain how the number of each subatomic particle is determined for boron and aluminum. Well, for boron, okay, atomic number is going to be 5, and its weight on the periodic table, its average weight, now careful, its average atomic weight is like this. So protons, we know, is going to be 5 protons. Also, every proton will attract an electron, so we're going to have, I should say, 5 protons and 5 electrons. Now we have to subtract. We've got to round this off to 11 minus 5 is going to be 6 neutrons. Because this is the weight of the nucleus, we subtract 5 of those. For aluminum, we have atomic 13, and I believe the average atomic weight is 26.9. Oh, pardon me. So we got 13 protons, 13 electrons. because the protons and electrons will be equal. We're going to round this to 27 minus 13. We're going to get 14 neutrons. Let's see, what do the sum of protons and neutrons in an atom equal? Well, if you can take a look at a specific atom, the sum of protons and neutrons is the mass number. It's specific. Okay, it's like your weight is different from everybody else's weight. Different atoms have a specific mass. Different isotopes of atoms have a specific mass. And they're all relative. Everything on the periodic table is relative. They compare it to the weight of carbon, carbon-12. So it's relative to carbon-12, the most common isotope. That's what they're using as a basis to measure all that. What are isotopes? Okay, isotopes are atoms of elements. I'll use the E for elements. That are heavier or lighter. Okay, so you might have like hydrogen 1, hydrogen 1, which only has no neutrons, hydrogen 2 that has 1 neutron plus 1 proton, or maybe hydrogen 3 called tritium. It has 2 neutrons and 1 proton, so that's why they call it hydrogen 3. They differ the number of neutrons. And why does the atom's mass number not equal? Let me zoom out here, make sure we get that. Why does okay, so the mass number does not, atomic mass on the periodic, it's an average weight. It's an average for millions of atoms. Probably billions or trillions of atoms. Okay, but the main thing, it's an average number. Why the mass number is specific. Like for hydrogen 3, okay, it has 1 proton plus 2 neutrons, so its mass number will be 3. Now, when you look on the periodic table, the average atomic weight for hydrogen is 1.01. Almost all hydrogens are going to be hydrogen 1, the isotope where there's no neutrons, but there's a very few number of hydrogen 2 and 3, so it makes that average atomic mass just slightly bigger. Number 9, how is a modern periodic table arranged? It is arranged by increasing atomic number, which means number of protons. That's how it's arranged. Now, what subatomic particle determines the element's chemical properties? Well, because here's an atom here, okay, here's the nucleus, it's got protons and neutrons, but you've got all the electrons spinning around out here. It's the electron that's going to be most important in determining the chemical properties. Whether this one wants to bond with another element to share electrons, or whether it's like a noble gas where it's got 8 electrons out here and it does not want to bond at all. So it really has to do, the electron is going to be the most important part in determining the characteristics of an element. Now, true, the electrons are drawn by the protons, but it's the electron interaction that really makes chemistry happen. Number 10, what are the horizontal rows and vertical column? Okay, the horizontal rows, so that's going to be periods. You know what? Okay, so we got periods going this way. And there's 7 periods at Buchanan, 7 periods, 7 horizontal rows. And then groups go up and down, and that's what I like. Groups, G-R-O-U-P, up, they go up and down. But I think everybody's pretty much got that. Sometimes groups are called families. But sometimes, though, we will say, oh, you got the family here in the middle is the transition metals, which we might call many groups. But traditionally, a group or a family just goes up and down. Where are the following groups on the periodic table located? Okay, metals, nonmetals, and semimetals. Okay, well, we know we've got the zigzag line over here. Metals. You got nonmetals. And then touching the zigzag line, actually technically it's the elements touching the side of it. Those elements, let me go right there, make it a little bit better. Those elements are going to be the metalloids, also known as the semimetals, and they have characteristics of both in that they sometimes can conduct electricity like metals, but other times they don't. So, and the only exception to the rule is aluminum and polonium, but we're not going to stick you with that. So I think I got that. Give an example of an element from each group. Oh, well, okay, silver is a metal. And a non-metal would be selenium, okay, or silicon, like is a major component of glass. Actually, silicon's a semiconductor, so that would be a good one, because if you adjust it just right, it can conduct electricity. But if you adjust it another way with electrons, it'll not conduct electricity. And probably chlorine is a good non-metal, okay? What are the following groups on the periodic? Okay, the alkali metals are going to be these over here, and you should have your periodic. These are the alkali metals. Alk metals, except for hydrogen, it's not a metal. Then we've got the alkali earth metals. And let's see, what else is the other one we're asking you there? Okay, the transition metals are these right here. And look at how the transition metals have their own little spot in a periodic table. It's really neat how it's set up that way. Let's see, what do we got next? The halogens are these guys right over here. So the halogens are over there, group 17. And what do we got here next? The noble gases, also known as the inert gases, right over here. Noble, because like the ancient nobles of Europe and Asia, the noble people often would not interact with the common folk, so they're noble gases. Also known as inert, which means does not react. Did I get everything? And you know what? Down here, those are known as the rare earth metals. And specifically, the top group, since lanthanum is the first one they call them, sometimes the lanthanides, and sometimes these are called the actinides down there. But if you know these are the rare earth metals, you'll be good. Okay, number 13. Which group of elements has only full shells? Well, when we take a look at the periodic table, let me let the bell ring. Uh-oh. As we go across the table, 1 electron in the outer shell, 2 electron in the outer shell. Transition metals are weird, they have 1 or 2. Then we have 3, 4, 5, 6, 7, and then finally, these elements here have 8 electrons in their outermost shell, except for helium. It's too small to have 8, it has 2. So, to answer the question here, which group of elements has only full shells? It's going to be the noble gases. Which group contains inert elements? Okay, again, the word inert is noble gases, the noble gases. And what does inert mean? Inert means does not react. When I was in the Navy, sometimes they'd have test dummy bombs that the pilots would drop. They would say it stamped on it inert, meaning it was just a chunk of metal, it would not explode. What elements are second period elements? Well, okay, so here's the second period. They are the elements lithium, beryllium, and then boron through neon. And again, these elements have s orbitals, so, and then over here, these elements have their s orbitals, plus they're going to have the p orbitals as well. So, let's see, what elements are group 14? Well, group 14, you'll be able to use this periodic table right there. Okay, it's carbon through lead. So you just look on the chart there, and incidentally, these elements tend to have 4 electrons in their outer shell. And lastly, good, I got through it. Define atomic size. All right, well, atomic size, and they tend to do it when you have 2 atoms. Let's say this is hydrogen gas, and you take this distance here and divide it by 2. You'll end up with the average atomic radius right here. So it's the distance from the nucleus to the outer part of the shell. But that's kind of hard to tell sometimes because it can change. Electronegativity is the ability to attract electrons. Now, these elements over here, these guys have 7 electrons in their outer shell. They really want 1 extra electron. Because if they get 1 extra electron, they think they're going to be a noble gas. They'll be happy and stable. So these have really high electronegativities. Okay, I think the highest number is 4. When they calculate it, that's going to be fluorine. Really, really, really high electronegativity. It really wants electrons. And fluorine's going to be the strongest because it's the smallest atom, so its shells are closest to the positive nucleus, so it's really going to attract them. So for electronegativity, really high over here. And as we come across over here to the periodic table, these guys are trying to get rid of electrons. Metals tend to get rid of electrons to become stable. So their electronegativity, their ability to attract electrons is really low. They're almost little subatomic machine gun electron shooters. Ionization energy. the trend is the same as electronegativity, but the idea is ionization energy is going to be the energy needed to pull an electron off of an atom. And these guys over here, they really want to hold on to their electrons. So it takes a lot of energy. If I'm going to pull an electron off of fluorine, it takes a lot of energy. Now coming over here, sodium, it's almost going to throw them at me. I could just flick those off really easy, the outer electrons. They want to get rid of electrons. So they have a really low ionization energy because it doesn't take much energy to pull them off. And again, that's because as we go across the periodic table, these elements over here need more electrons to become stable. Because really, in all of chemistry, it's all about these atoms trying to get partners to team up with so that they think they're a noble gas. And with that, there's the end of number 15. Thank you for your attention.